In algebra, we think of functions as something like f of x, where x is the input, it's plugged into an equation, and we get some output f of x. In programming, we can also define functions. These also have inputs and outputs as well. Let's look at another way to view functions. Whether we're writing a function in algebra or in a computer program, functions will have inputs and outputs. We have a set of all possible inputs of f, and this is called the domain. We have a set of all possible outputs of f, and this is called the codomain. While working with functions in this section, we'll use this notation for a function, where f is the function name, a is the domain, and b is the codomain that is being mapped to. The function f associates one input from a with one and only one output in b. A mapping between a and b is known as the rule. It can be a mathematical expression like f of x is x squared, or even a set of ordered pairs like a as an x-coordinate with 1 as a y-coordinate, b to 2, and so on. An example of a function is the function p from a to b. This is a function that maps a phone number to a single person. Each person has a unique phone number. So set A could be a set of various phone numbers, and set B could be a set of people, and then our rule will be the mapping from the phone number to the person. We can view the rule as a set, or we can diagram everything out as I have below. Sometimes we'll have a function where the codomain or the domain is from an infinite set, such as the set of all integers. In this case, you only write out a few elements of the set for the domain and the codomain, and then draw some mappings between them. So here we have a function where both the domain and codomain are the set of all integers, and the rule of f of x is x plus 2. We can't diagram every single element, but we can diagram a few of them, so that's all we need. Besides an equation for the rule, we can also specify our mapping explicitly by just writing out a set of ordered pairs as our rule. So for example, for this one, the function g from a to b, where a is 1, 2, and 3, and b is x, y, and z, the rule here is 1 maps to z, 2 maps to y, and 3 maps to x. And then the diagram below is how this would look. So now you can practice. Diagram the following function, the function h from x to y, where the set x, the domain, is 2, 4, 6, and 8, the set y, the codomain, is 1, 3, 5, and 7, and the rule is 2 to 7, 4 to 3, 6 to 5, and 8 to 1. Here's what the diagram should look like. Notice that I have labels for x and y, and all of the arrows go from the domain to the codomain. In mathematics, a binary relation on a set A is a collection of ordered pairs of elements of A. In other words, it is a subset of the Cartesian product A squared or A cross A. More generally, a binary relation between two sets A and B is a subset of A cross B. So in other words, a binary relation R from sets A to B has a subset of the Cartesian product A cross B as its rule. So let's say we have the set A, which contains 1 and 2 as its elements, and the set B, which has A, B, and C as its elements, and we have some relation R from A to B. The rule can be all of A cross B, such as 1 to A, 1 to B, 1 to C, 2 to A, 2 to B, and 2 to C, or it can just be a small subset of A cross B. So for example, 1 to A, 1 to C, and 2 to B. These both would fit the definition of a binary relation. So let's say we have A is 1 and 2, and B is A, B, and C, and our relation is R from A to B. And if we have the rules 1 to A, 1 to B, 1 to C, 2 to A, 2 to B, and 2 to C, which is all of A cross B, our diagram will look like this. So now let's practice. Given those same sets, A is 1, 2, and B is ABC, and the relation S with the rule 1 to A, 2 to B, and 1 to C, diagram this relation. This is what your relation diagram should look like. If a binary relation has the same set as the domain and the codomain, we can diagram it with the arrow diagram or with a graph like this. Diagramming like this will come in handy later when we have more complex relations. So see if you can figure out how to diagram it this way. Practice by finishing the given diagram for the following relation. The set A is 1, 2, and 3. The relation R is from A to A. And the rule is 1 to 1, 1 to 2, 1 to 3, 2 to 3, and 3 to 2. This is what the finished diagram should look like. If any element points to itself, such as 1 to 1, then it will just have a loop around back to the same node. Now remember that a function must map each value from the set A to one and only one value from the set B. A relation doesn't have this restriction. With this diagram below, it's a valid relation, but it is not a valid function because 1 points to both A and a C. The element from the domain 1 is not pointing to one and only one element in the codomain. So knowing that a function associates one input from the domain with one and only one output in the codomain, identify whether the following relations here diagrammed are also functions. For the first diagram, this is a valid function. Each input from A maps to one and only one output in B. It is okay that the output B doesn't have anything mapped to it. For the second diagram, this is not a function because the input value 2 maps to two different outputs, B and C. Number 3 is a valid function. And number 4 is not a valid function because the input value 1 is not being mapped to anything. While there can be elements in the codomain that are not being mapped to, everything in the domain must be mapped to something. We can also take the inverse of a function or a relation. So, given some relation R from A to B, we can say that the inverse is the inverse of R from B to A. We also reverse the mappings, so a map from input X to output Y would become a mapping from Y to X in the inverse. For example, say we have the relation R from A to B, where A is 1, 2, and B is ABC, and the rule is 1 to A, 1 to B, 2 to B, and 2 to C. Its inverse will be from B to A, again with the same A and B sets, but now the mapping will be A to 1, B to 1, B to 2, and C to 2. Notice also that I keep drawing the domain in the left side and the codomain on the right side, so in this case, for the inverse, the set B is diagrammed on the left as the domain. Also keep in mind that the inverse of a function will not always also be a function. So for example, in the case where we have an element in the codomain not being pointed to, this could still be a valid function, but when we invert it, that element from the codomain becomes an element of the domain, and so the inverse is not a valid function. So let's practice. Diagram the following relation and its inverse. So we have the relation R from A to B. A is 1, 2, 3, B is X, Y, Z, and the rule is 1 to X, 1 to Y, 1 to Z, 2 to X, 2 to Y, and 3 to Z. The inverse will be from B to A, and the mapping will be X to 1, Y to 1, Z to 1, X to 2, Y to 2, and Z to 2. So here are the diagrams for both the relation and its inverse. For a function f from A to B, writing out the ordered pair xy in f means that the input x from A is mapped to the output y from b in the rules of the function f. So the value x is from a, we can write x is in a. The value y is from b, so we can write y is in b. And the mapping from x to y exists for the function, so we write that the pair xy is in f. Another type of problem you'll see is like this, so let's step through it really quick. Diagram the relation R from A to B, where A is the power set of the set 1, 2, 3, and B is the set 0, 1, 2, and 3. The rule is that the pair xy is in the relation R if the size of set x is equal to y. So first, let's look at the domain A. The domain A is the power set of the set 1, 2, 3, and this means if we expand it out, we get a set containing empty set, the set that contains 1, the set that contains 2, the set that contains 3, the set that contains 1, 2, the set that contains 1, 3, the set that contains 2, 3, and finally the set that contains 1, 2, and 3 together. Remember that the power set is basically the set of all possible subsets you could build from that original set. Secondly, for the rule, it's saying that the relationship between x and y exists in our relation R if the size of set x is equal to y. So in this case, x is any input from the domain, so it could be the empty set, the set containing just 1, the set containing 1 and 2, the set containing 1, 2, and 3, and so on. So n of x would be the size of that set. For empty set, the size is 0. For the set that contains just 1, the size is 1. For the set that contains 1 and 2, the size is 2. And the set that contains 1, 2, and 3, the size is 3. We're going to compare this size to a value in the set B, the codomain, which will be either 0, 1, 2, or 3. So essentially, if the size of the input set matches the value from B, then the relationship exists, and you draw an arrow between it. So to reiterate, if we choose some arbitrary input value x from the set A, we might have something like the set that contains 1, or the set that contains 1 and 3, or the set that contains 1, 2, and 3, and the relationship between the value x and some output y exists if the size of the set x is equal to the value of y. So if we choose the input x equals the set that contains 1 and 3, it has a relationship with the output y equals 2. The size of the set 1, 3 is 2, so that's where the relationship works. Now, it won't have a relationship with y equals 0, or y equals 1, or y equals 3, so there will only be an arrow between the set that contains 1, 3, and the output y equals 2. So, given this information, try to finish this diagram. This is what that diagram would end up looking like. So the empty set is size 0, and so it points to 0. The sets that contain only 1, or only 2, or only 3, each of these is size 1, so they each only point to the 1 in the output. The sets of size 2 point to the 2, and the set of size 3 points to the 3. Let's try to practice one more time. This time we have the relation R from A to A. The set A is 1, 2, 3, 4, 5, and 6. And we have the rule that there's a relationship between input x and output y if x minus y is a positive even integer. If we write out the domain and codomain separately in our diagram, it will look like this diagram on the left. Or if we want to use just the nodes, we can use the diagram on the right. So this was quite a bit of information. None of it was terribly difficult, but it can be hard to keep track of everything altogether. Make sure you understand these core concepts before moving on to the next topics. Next time we'll talk about properties of functions and properties of relations.